So again we will consider this fictitious device which has two control terminals and two output terminals. This is the gate, the first source, the second source and the drain. Okay. ID is a function of VGS1, exactly like in a MOSFET, except that we have separated the controlling side and the control side. The last alternative that was left was to sense the current at the source and feed it back to the source, feed it back to the gate. Okay. So what we do is, this is our desired current I0, and I0 minus ID tends to flow in this branch through the parasitic capacitance. Now let us say S1 is connected to some fixed voltage and you have to change the gate voltage. So what happens to the source voltage if I0 is more than ID? What's that? It decreases. And what do you want to do to the gate? Decrease, increase. If I want to increase the current ID, I have to increase the gate voltage when source voltage is fixed. So what kind of a block do I need between this and the gate? Some negative gain, so that when the source voltage increases, the gate voltage decreases and vice versa. Okay. So this will work. The only difference between this and what we can realize in reality is that we really do not have separate controlling side and control side. The sources on two sides are the same. Okay. So the circuit, the sources are also connected together. So if I redraw this, looks like this. Because of the source connection, there is also feedback to the source itself. If you recall the third circuit, what we did was, we had this and a comparison of current, and we connected this to a fixed potential and connected the sources together. Okay. So this actually has feedback both to the source and to the gate. Okay. It has feedback to the source because of the implicit connection between the input and output side. It has feedback to the gate through the amplifier. Is it okay? We will see practical realizations of this soon. So it turns out that, as before, if you want negative gains, you can use a common source amplifier. Okay. We will look at it shortly. So we have four types of biasing. The first, one particular realization of it was this. The second one, rather let me draw the more general thing first. So this plus indicates positive gain. This minus indicates negative gain. And it's assumed that I0 is connected to the, or coming from the power supply. This is the third one. And this is the fourth one. Okay. A very common practical realization of the first one is what is known as a diode connection. It's called a diode connection because if you make the same connection with a bipolar transistor, okay, you connect the collector and base together, you will end up with a two-terminal device which follows the IV characteristics of a diode. Okay, in fact, it follows the IV characteristics of a diode better than the diode itself. So that's why it's a diode connection. Okay. So, and for the second one, is this. The third one, I mean, that itself is the most practical form of it. You have to find the current source somewhere, but once you have a current source, you can connect it up like this. The fourth one, I will not write the complete circuit now, but you can in fact do something of this sort. Okay. I will not yet complete where this is going, where the drain of the second transistor is going. In all these cases, we started off with trying to bias this transistor M0 with a current I0. In this case, we have an additional transistor M1, which also happens to be biased at I0. Okay. Here also we have M0 and this is M1. We haven't shown the biasing for M1 yet. We will look at it soon. Okay. Yeah. Yeah. If the drain was? No, it will not be the same as the third case because see, whatever it is, this will also have feedback to the source. The question was if the gain of amplifier is -1, is the circuit exactly the same as this? No, this circuit is exactly the same as this if the gain of the amplifier is 0, right? Because if the gain of amplifier is 0, then the gate voltage is fixed. So only then will that be the same. So there is always feedback to the source. This amplifier represents the amount of feedback to the gain. I mean to the gate rather. Yeah, actually all of these, when you make up the complete topology, you can use it for different things. Okay. So for instance, I think here in the second case we used an op-amp, right, to provide this feedback. In the fourth case also we can do that. Let's see what happens if we do that. Yeah. Not the MOS transistor, the bipolar transistor. So there are a couple of reasons. I will get back to you about that. So first of all, one thing is a practical diode always has some resistance in series with it. Okay. So if you look at the voltage drop here, let's say certain current I is flowing. Okay. The voltage across this is Vt ln Id by Is. The voltage across this is Id times Rs. Okay. So the actual Vi relationship is, I'll still call it VBE, although this is a diode. Vt ln Id by Is plus Id times Rs. Now if you do this and you have a series resistance here, okay, what happens if you apply a voltage here that appears across the base emitter? Okay, so the drop across this resistor does not affect the exponential, right? this current is still Is exponential Vb by Vt. Yeah, that's correct. So how much will it show up? So let's say this is the resistance. Okay. First of all, the emitter is the most heavily doped and collector is the least heavily doped. Right. So the collector resistance is the highest and emitter resistance is the smallest. Okay, at least among the two, emitter resistance will be the smallest. Right. Collector area can be very large. It can be a long contact also. So you have Rb. So you have some, this current is now, this voltage is now Vt ln Id by Is. Okay, what is this drop across Rb? So Vt ln Id by S plus Id Rs, let me call it Rs also, divided by beta. So the parasitic drop is much smaller in this case, and also there is some thing with something I don't understand very well, which gives you for large current densities, the current in a diode becomes Vb by some this thing, which is where this is approximately 2. Okay, whereas the same thing doesn't happen with the bipolar transistor. So the bipolar transistor follows the exponential Vb by Vt much better than the diode connection. That is, when you have only two, when you just have N and P, it will be much worse than if you have NPN and then use one as the controlling terminal and connect the controlling voltage to that one. Okay. So this one, I have read about this, but I have forgotten the physics behind it. Yeah, but I don't know why it doesn't happen in a bipolar transistor. Okay. So if you want to make a good diode, it's better to make a transistor and do this. Okay. And when you have bipolar transistor technologies, you will use diodes for different things, and this is how you do it. You normally don't use just a junction of two semiconductor materials to get a diode. You will make a bipolar transistor and connect it up as a diode. So for the second case, we made a circuit like this, assuming we have an op amp. Something like this, right? And the drain will get biased at Vd0 if it's an ideal op amp. So similarly, for the fourth one, for the amplifier, we can use which is plus and which is minus? Which is the plus? Plus is on the top. We want a negative gain from source back to the gate. So this is in this direction. So what is the source voltage now? V0, right? So if we have an ideal op amp, this will be exactly at V0. So now one thing you can do is, this voltage is now fixed at V0. Okay? So I had earlier said that let's not worry about where the current source comes from. Let's assume that there is a current source somewhere. Okay? So if you have a fixed voltage, how will you get a fixed current? Just put a resistor. Okay? So in fact, you can use this circuit to make a current source when you don't have any current sources at all. So if you, by virtue of negative feedback, the source voltage is always at V0. Okay? So I don't have to use a current source with infinite output impedance. I can use a very lousy output impedance and still the current will be constant because the voltage is fixed. So if I use some R0, if I just use a resistance, then the current through this will be V0 by R0, and then I can use this in other places. Okay. So, I can make a current source. This can be thought of in different ways. Sometimes you need some current source proportional to a voltage. Or you can think of it as inversely proportional to R0. That is also useful for many things. Okay. Whereas in the other case, this will not work. At least this will not work very well. Okay. Any questions on the 4 schemes of biasing we discussed so far? First one. Oh, see, in this schematic, the source is connected to the op-amp output. It's assumed that the op-amp output will deliver whatever current that flows out of the source. I mean, that will absorb whatever current flows out of the source. Okay. So, then there is no problem, right? See, finally when steady state is reached, this I0 will flow through this this transistor M0. So, the source node will get adjusted to a certain voltage. What is that? That is Vc0 minus Vt plus the overdrive corresponding to I0, right? Now, this current has to flow through the op-amp. If you assume an ideal op-amp, it can deliver any current and take in any current, so there is no problem. When you make a practical circuit, an implementation of this op-amp, it has to be able to absorb this. Okay. Now, the one practical incarnation of this we saw was this one, which in fact can absorb that current. Okay. Gain of the amplifier, which amplifier will be? That's not, we are using M1. The idea is to bias M0 at I0. We have not yet said what we have used M0 for, right? First of all, yeah, we have not yet come to how to use it as an amplifier. See, if you have inductances and capacitances of arbitrary values, and if you assume that your signal is only at AC, not at DC, you can change any of these circuits so that at DC it looks like this, and at AC it looks like any amplifier you want. Okay. So, for instance, but that's not how we use it. In fact, this circuit, what you say is right. This is not very nice. This is not suitable for using M0 as a common source amplifier. Okay. But if I really wanted to, and if I had infinite liberty with my choice of components, I could do this. So, this will ground my source for incremental, small signal increments, right, as long as they are at AC. So, then I can apply Vg0 plus my input voltage and take the output from here. Okay. Of course, this is not practical at all, but if I really wanted to do it, this is how I would do it. Which one? This one? We will see soon. So, what we saw so far was if you have a current source and a MOSFET, you can make the drain current of the MOSFET equal to the current of the current source. Okay. Now, each of this is suitable for different applications, and you use whichever is convenient in a given application depending on the topology. Now, there is one more way in which you can bias transistors at a given current on an IC, because earlier we had said that on IC components match very well, okay. And also for a MOSFET, VGS is the controlling quantity and ID is the control quantity. So once you have one MOSFET biased at a given current, you can replicate its VGS to other MOSFETs and get the same bias current, okay. So that's yet another way of biasing a transistor at a given current. This assumes that there is already another transistor which is biased at the desired current, okay. Then you simply replicate VGS and then you will replicate the current as well. Now there will be some errors because of random mismatch, but that we will ignore, okay, or at least we know how to calculate that already. We know how much random mismatch is there in different parameters of the MOSFET. So we can put that into our circuit and see how much effect it has and whether we have to improve the amount of matching, okay. But replication is the fifth way of biasing a transistor at a given current. Once you have any of these circuits, you can replicate the VGS that you obtain here to other MOSFETs and get the same current, okay. So we can try that and see what all the circuits that we get. So one other thing you have to observe here is already with such a simple idea to bias a transistor, the number of circuits is exploding, okay. So you have to just understand a few principles. You will not be able to remember everyone, but you understand all of these basic stuff, and any complicated circuit that you derive will be some combination of these basic circuits, okay. So for instance, like here I have this amplifier, okay, and here also I have the amplifier. This amplifier could be part of some other circuitry that I want to do, and it just happens to be around the transistor M0, okay. So to get the same current, replicate VGS to other MOSFETs and you will replicate the current as well, okay. And this is possible for all four circuits. Whether it's convenient in a given occasion or not is up to you, but you can do it for all of them. So the very first circuit was this. I censored the drain and feed it back to the gate. And to replicate the VGS, I have to connect the gate source of another MOSFET across this, okay. So this is the classic current mirror, but what is happening here is that through feedback you adjust the gate source voltage of M0 and then you replicate it to many other transistors. In case of MOSFET, because the gate current through the MOSFET is 0, you can connect any number of MOS transistors without affecting this voltage, okay. So obviously that's a condition, you can't be affecting that voltage. So let's say this has a certain aspect ratio, this has the same aspect ratio. So what will be the current here? It will be the same, I0, okay. Now if we ignore channel length modulation, it will be the same I0. If you have channel length modulation also, depending on the voltage at the drain of the MOSFET, the current will change a little bit. We will see how to get rid of that also. Now one thing you can do when you replicate it is that the square law says that the current is this much, okay, and matching says that Vt and these quantities are the same for all MOSFETs, okay, all MOSFETs on a given chip, and replication of VGS says that this is also the same. but there is no need to keep this the same. Okay. So you can change the aspect ratio and get a certain multiple or a certain submultiple of the current. So the current in a MOSFET is proportional to W by L. Now one thing that you should keep in mind while replicating is the fact that ID is proportional to W is exact. Okay. If you take two MOSFETs and connect them in parallel, you do get twice the current. But ID is not exactly inversely proportional to L, because the drawn length is different from the effective length, and when you make different lengths, the ratio between the drawn length and effective length is also different. Okay. So the inverse proportionality to L is not exact, but direct proportionality to W is exact. For instance, if we had transistors in velocity saturation, what's the current? What is the current expression in velocity saturation? I think that's what it is. Okay. Is there a divided by 2? I think, yeah. So in this case also, clearly here the current is not dependent on L at all, right? Whereas it is directly proportional to W. So when I said you can change the aspect ratio and change the current, I really mean that you can change the W and change the current. Okay. Clearly, if you take a long MOSFET here and a short one here, this could be in velocity saturation or partly in velocity saturation, whereas the other one is not. So if you change L, your replication is not guaranteed, but if you change W, it is, right? You keep the same length for all the transistors and then you change Ws, you will get currents that are proportional to the widths of the MOS transistors. So this is a general rule you have to follow whenever you are expecting to scale currents with aspect ratio. Okay. So I have W1 by L0 here. So what's this current? What is the current through this transistor? So it's I0 times W1 by W0. Okay. So if you want twice the current, you make W1 twice W0. And while discussing systematic and random mismatch, I had said that to get twice the width, the best thing is to make two fingers and put them in parallel, right? Not make two MOSFETs like this. You don't want to do, this is W1 and this is W0. This is not what you want. Okay. You should make 3 of these and then connect 2 of them in parallel. Okay. So instead you should make something like this. So these are the gate fingers. You connect these two and you connect these two as the source and this is the drain. Okay. So this is the layout of the MOSFET. So this will make sure that matching is good. So when you have an integer ratio, you can do this. When you have non-integer ratios, you just have to take the hit in accuracy. Okay. You cannot make it. So for instance, if you want 1.5 times I0, that may be okay because this is 3 by 2. So you can put 2 fingers here and 3 fingers here. But if you want some arbitrary ratio like 1.875 or something, it may be too complicated to do this. So depending on the accuracy requirement, you just make the MOSFET with a slightly different width and go with it. Is this clear? So you can, once you bias a MOSFET at a given current, you can replicate its VGS to other MOSFETs and get scaled versions of the current. And while doing scaling, you should scale the width, not the length. Okay. The only time you scale the length is in some extreme condition where you can't scale the width at all. And then you cannot rely on the accuracy. Okay. And also it will vary with process and temperature. The dependence on L is not exact. The dependence on W is. Okay. So the idea is to replicate VGS to other MOSFETs of same length and scale W to scale currents. So you can, the VGS replication is exact. What is different can be that the drain voltage here is different from the drain voltage here. So the currents through the two MOSFETs will be different. The current through this one will always be I0. That's because of negative feedback around M0. Okay. Whereas the current through this will be some scaled version of I0 because you will have 1 plus lambda VDS1 here and 1 plus lambda VDS0 there. Okay. So this current will be I0 times 1 plus lambda VDS1, where this is M1 by 1 plus lambda VDS0. If so VDS1 is different from VDS0, you will get an error in the current replication. So to get exact current replication, you have to also make sure that the VDSs are equal. In fact, the following circuits that we will go through will make sure of that. Yeah.
And then we again have a transistor. We take this gate connection and then have a single transistor.
Yeah. So that won't make any. Okay. What's the question?
Basically, what is dark side transistor is W by 2L, but the other one is W by L.
So the question is this: instead of making a single transistor of length 2L, you connect two transistors in series. Okay. And then you have one transistor on the other side. Okay, let's say all of them have the same W's. The question is whether the current here will be double the current here. Okay, again it's not true. So this combination behaves exactly the same way as a single transistor of a longer L. Okay, so for instance, it is the field here is smaller. Right, because the voltage here is smaller. So the arguments about velocity saturation, etc., apply here also. It could be that this is not in velocity saturation and this is in velocity saturation. Okay, or this is less in velocity saturation and this is more in velocity saturation. The fact that this is W by 2L itself is approximate, right? That if both of them follow the square law, you can get that. Otherwise, it's not the case.
So basically, if the VGS is not very high, so that we push both the transistor into velocity saturation, or one transistor into velocity saturation, then still the rule would apply.
Yeah. So first of all, the rule would apply simply because the drawn length and this thing is not equal. You try to make the ratio of drawn length and the fabricated length equal by splitting it, right? Is that what you are trying to do here? Yeah.
Okay.
So that goes away.
Yeah, that goes away.
Okay. But still, the fields inside are different. The inverse proportionality to L again still does not hold. Only if you have very long channel transistors. Okay. If both are very long channel transistors, it will work. So let's say you have W0 by L1, W0 by L2, and both lengths are very long. Okay, then the currents will be in the ratio L1 by L2. So if the velocity saturation depends both on VGS as well as the channel length. Okay. So the square law was derived for a very long channel transistor, a long channel transistor. Okay. So that if you use, and in modern technologies it doesn't hold, and you can try it. You can simply try even something like 0.4 micron length and 0.8 micron length, which in fact is a long transistor for a 0.18 micron technology. Okay. So even then, I don't think you will get good replication.
So in this topology, we know that because of this difference in the field, there will be error.
Yeah.
Other than that, because of packet bias.
No, that should be the series connection of two transistors is the same as a single transistor. Okay. So if you think about it, the question is the backgate bias here is different from this. But if you look at the MOSFET, that is true here also, right? I mean, you connect the bulk to some potential. So if you think of this as the upper MOSFET and this as the lower MOSFET, the backgate here is connected to ground and here also it is connected to ground. So that's how it should be. In fact, if you take this backgate and connect it to source, it is not equivalent to two MOSFETs in series. Is that okay? So only if you connect it to ground is it equivalent to a single long MOSFET. See, if you connect it back to the source here, that means that somehow this backgate is connected to this point. Okay, in the middle of the MOSFET. That's not what really happens. Anything else? So there are other bias sources to be discussed. So everything can be replicated. In every one of these cases, you can take VGS here or there and then you replicate it across other MOSFETs. Okay. We will in fact discuss some of those circuits. But before that, we discussed two types of amplifiers, that is the common source and the common gate amplifier. Okay. That is, I have some amplifier with a negative gain and I have a current buffer. So as you very well know, there is also a third type of amplifier, the common drain amplifier. Now, you can think of the common drain amplifier as a voltage buffer, right? So let's say I have a current buffer and I want to get a voltage buffer, and let's continue to think about this fictitious MOSFET with a separate controlling terminal and a controlled terminal. Okay, that is, I have gate source 1, drain and source 2. Okay, the small signal equivalent of that will be, if I apply VGS1, okay, let's continue to ignore the body effect. This is a fictitious device. What I am trying to do here is to motivate the existence of common drain amplifier. Okay, so I have a voltage amplifier, that is the common source amplifier, and I have a current buffer. So maybe I need a voltage buffer also. So how will I make a voltage buffer or a voltage follower if you have an op amp? How will I make a voltage follower with an op amp? So I should use feedback with no feedback fraction or feedback fraction of unity. Okay. So this is what I would do, right? Now this, what is the voltage here? Minus Gm by Gds times VGS1. So I have something like an amplifier. Okay. In fact, I have two input terminals and two output terminals. How will I make this circuit? Using that. See this, what is inside the op amp? I have the input terminals and I have a control source Okay. And this side I ground, and this side I connect here. Okay. So this is the op amp. This ground connection is implicit inside the op amp. This the connection here. So similarly, I can do the same thing here, right? So I connect it, and I ground this. This is equivalent to this one. Okay. And I apply an input here, and I get the output there. Is this okay? So I do the same with the MOSFET. So what do I have to do? So it just turns out that I have to connect S1 and S2 and ground this side. Okay. Now in a real MOSFET, S1 and S2 are already connected, isn't it? So I can make a voltage follower by simply grounding the drain, applying an input to the gate, and looking at the source voltage. So this is the incremental equivalent circuit of a voltage follower. I will now draw it with the conventional MOSFET equivalent, not with separate sources on input and output side. So this is the gate, drain, and the source. Okay. So this is the small signal equivalent of a voltage follower, or in this case it's called a source follower because the source voltage follows the gate voltage. Okay. So, or in the signal picture, that should look like this, right? The drain should be grounded, and you apply an input to the gate, and you look at the source. So you can think of the source follower as being derived from the common source amplifier when you attempt to make a voltage follower. Okay. You try to use negative feedback around a common source amplifier and get a voltage follower, you will end up with the common drain amplifier or the source follower. Is this okay? So what is the gain of the circuit? Now that we have derived the topology, you have to do more detailed analysis to see what the gain is. So VGS is nothing but Vi minus Vo. Okay. Now I just write the current balance equation and find out. This current is V0 times GDS, and this current is GM times Vi minus Vo. Okay. So V0 by Vi turns out to be GM by GM plus GDS. Or GM by GDS by 1 plus GM by GDS. Okay. You can also observe that the last expression is of the form loop gain by 1 plus loop gain, and in this case we use the common source amplifier as the forward amplifier. So its gain turns out to be the loop gain. So it's GM by GDS by 1 plus GM by GDS. What happens if I connect the load GL? So you can see that GL is directly across GDS. These two are in parallel. Okay. So wherever you have GDS before, you will have GL also. Okay. So the magnitude of V0 by Vi is approximately 1 as long as GM is much more than GDS and GL. Okay. So one thing that is left out is that we assume that the source is connected to the bulk is connected to the source. So what happens if the bulk is not connected to the source but is connected to some fixed potential? If the bulk is connected to the source, I don't have the other incremental source there, current source. So now I'll also have that. This is the drain, gate, source. Bulk is connected to a fixed potential in the full picture or ground in the incremental picture. So is the drain. And I will not use some GL. If I do have it, I can absorb it with GDS. Okay, if I have a load. So what is V0 by Vi in this case? So this current, the control source from the bulk transconductance is GMB times VBS, okay, which basically is, what is VBS in this case? Minus V0, okay. So this is a source of GMB times V0 pointing upwards, and it is connected from V0 to ground. Okay. So the controlling quantity is across the controlled source is across the controlling voltage. So this is equivalent to a conductance GMB. Okay. So if I connect GMB here, the current flowing here will also be GMB times V0. Okay. So GMB simply appears across GDS. V0 by Vi is GM by GM plus GMB plus GDS. Okay. So in this case, if the bulk is connected to a fixed potential instead of the source, the gain is not necessarily 1. You can have GM much greater than GDS. That's a reasonable assumption. But GMB by GM can be a significant quantity. Okay, it can be some 1/3 or half or something of the sort. So when you have a source follower with the bulk connected to ground, the gain will not be 1. It will be substantially less than 1. It can be 0.7 or something of the sort. Okay. So this is something you have to watch out for, and I've already said several times that in typical technologies you can connect the source of a PMOS transistor, the bulk of a PMOS transistor to its source, but not necessarily for the NMOS transistor, because all NMOS transistors share a common bulk. Okay, you can't connect each one to its own source. So when you make an NMOS source follower, typically you have this problem. If you have a PMOS source follower, you can connect the bulk to the source and get rid of this problem. Okay. So if you want a voltage follower with whose gain must be 1, you have to use a PMOS source, PMOS transistor. Okay. So I introduced this because this is also useful in the discussion of biasing stuff, and we have to do it at some point anyway. So we'll continue this in the next class. Also here you can see that GMB is not a good thing, right? For the common gate amplifier, we saw that it made it better. It made the input impedance better and it made the output impedance better. Whereas for a common drain amplifier, it makes it worse. Okay, it makes the gain worse. Is it okay? So what happens if you load a common source amplifier with a capacitance? Have you seen this circuit before? Huh? Yeah, this was also in assignment 1. So you have the capacitance of the transistor and this. The assignment 1 asked you to calculate the input impedance of something like this, right? So what was the result? Negative resistance. So one of the risks of using a voltage follower is that on the input side you can see a negative resistance. Okay, so you can have an oscillation problem with a stability problem with a voltage follower.